Welcome back to Science Click. Today, the mathematics of general relativity, Part 2, Space-time velocity. We are now able to describe the position of the apple through two coordinates on the grid. As we saw, we interpret the world line as a movement while proper time goes by. The coordinates of the apple which describe its position evolve, they depend on proper time, and it is therefore interesting to define the notion of velocity. The velocity of the apple in spacetime is an arrow, a vector tangent to its trajectory, whose orientation follows its movement. The length of this arrow encodes the speed of the movement. This speed is the same everywhere, because the intervals are regularly spaced along the world line. For a given proper time, the apple always travels the same distance. More generally, all objects in the universe move with exactly the same speed. It is a universal constant which we call the speed of light, denoted by the letter c. Therefore, we can write our very first equation, which states that the length of the velocity, its norm, is always equal to the speed of light. When using coherent units, for example if we measure time in seconds and distances in light seconds, the speed of light is precisely 1. This simply means that time is a measure of distance. The proper time of an object simply measures the distance travelled through space-time. For each second of proper time, the apple travels 1 light second through space-time. We now want to describe velocity using our coordinates. Starting from the apple, we draw 2 arrows on the grid that represent the directions and amplitudes of each coordinate. These arrows are called basis vectors. We will denote them E0 and E1 given the coordinates they respectively describe. With these 2 basis vectors, we can decompose the velocity as a sum. Here, for example, 2 blue arrows and 1 red arrow. The numbers 2 and 1 are called the components of the vector. The value of a component indicates the rate at which the corresponding coordinate increases. In a way, we measure the rate at which the apple moves along each of the 2 coordinates as proper time goes by. More generally, we can write the velocity vector as the sum of its components multiplied by the basis vectors. In mathematical expressions in general relativity, it often happens that a same term is summed over all coordinates one by one. For example, in the previous equation, we wrote the vector as the sum of each component multiplied by each basis vector. To compactify this expression, we can summarize the whole sum by writing only one of these terms and replacing the numbers which designate the coordinates by a Greek letter. For example, alpha, which goes through each coordinate one by one. This is the Einstein notation. When a Greek letter is repeated twice, once up and once down, it actually stands for a sum in which this Greek letter is replaced by each coordinate one by one. Let's illustrate this concept of space-time velocity using a concrete example. We imagine a satellite in a circular orbit around the Earth. When viewed from a distant position, the movement of the satellite can be described using 2 coordinates: time that we measure on our clock, t, and an angle, phi, which describes the position of the satellite around the planet. Looking at its world line, we can plot the velocity of the satellite at each point. This vector can then be decomposed with our 2 coordinates. The first component gives us its temporal speed. It is the rate at which our time passes compared to the satellite's proper time. If this value is 2, for example, this means that for every second that passes for the satellite, 2 seconds will have passed for us. The second component represents its angular speed. It is the rate at which the angle formed by the satellite around the Earth increases. If its value is 10 degrees per second, this means that for each second of proper time, the satellite moves 10 degrees around the planet. The first equation we obtained before allows us to say that the length of the vector is always the same. This is the speed of light. At a glance, one might think that we can use the Pythagorean theorem to calculate the length of the velocity given its components. But it is crucial to understand that the coordinates do not represent real distances. Their values and their rate of change are arbitrary numbers which do not have real physical significance. For example, the angle formed by these two satellites increases at the same rate. Their velocities have the same angular component, but it's easy to see that it doesn't mean they have the same speed. The farthest satellite moves faster, even though its vector has the same component. In the next videos, we will see how to solve this problem, how to get a real measure of physical distances and speed from components, building a new version of the Pythagorean theorem, more general, which works in spacetime regardless of which grid we use.